Okay, I think then we can start our class today. So we previously discussed about the sampling from mathematical point of view. Now we want to move to the circuit that perform the sampling task for us and see what are the issues that we have in this circuit. Okay. So basically, you remember that the sampling converts the continuous time signal to a discrete time signal. So we convert from continuous time into discrete time, and those samples, they will come at every TS of our sampling clock. So the sampling basically instances are defined according to the clock. So how frequent you want to have sample is depend on your sampling clock. And the clock basically again is controlling this switch here. In this is the simplest sample and hold circuit. So it has a switch and a capacitor that we hold the value to for the next clock cycle that comes. Okay, so how it operates when the clock signal is high, we assume that the switch is basically closed in this case. So it's conducting, and the Vn is being either charged on the capacitor, or if the capacitor has a previously higher values, it discharge into Vn. So the V out will equal to Vn. This is V out, the voltage on the capacitor. And as you can see here, this is the Vn. During this, when the clock is high, the V out is following Vn. Now, when the clocks become low, this switch is basically open, and we are in a hold mode. So we expect from the capacitor that it will hold the last sample that it has captured from the Vn or from the Vn, and keep it until the next time the clock becomes high. Once the clock becomes high again the V output will start to track exactly the Vn values during that, and once the clock will go down, it will hold the last value that it captured from the Vn. So this is how it's supposed to work the sample and hold circuit. In reality, it's a track and hold, means we are tracking during the on time of the switch. We are tracking the input voltage, and once we close the switch, once we open the switch, then we are holding the most recent value that was stored on the capacitor that we got it from the Vn. So in reality, it's a track and hold, but it's generally known as sample and hold circuit. So if we look at it furthermore, one more time. So if I have a clock here, let's show the clock. It's very difficult to draw. So this is the clock running on a frequency of Fs. So now in this case here, we have a hold, track, hold, track, hold, track. So when the switch is, let's start from the tracking phase. When the switch is on, the V output here is in the dark line, is tracking the V input. Now, once we go into the hold phase, the clock went low here, then basically what happens, we are holding the last value that was stored on the capacitor. Now again, I go into track mode, then we start to follow the V input, we go to the hold, we hold the last value, track mode, we start tracking input again, hold, we hold the last value, track, we track, and then finally we hold. So this is the track and hold circuit. And the sample and hold, you basically, the concept, if you just really stick to the meaning of a sample and hold, you sample the value, let's see here, you sample the value at the rising edge of this clock, and we keep it till the next time, or you sample it here, sorry, and we keep it till the next clock cycle. So again, we track it. What's happening here? We track it, and then we hold, not track it, we sample it, and then we hold it for the entire cycle. We sample this value, we hold it for the entire cycle. But in general, I mean, we are doing a track and hold, this one approach more, because at the end, we are just caring at the value that we are holding at the capacitor. So whether it was sampled one time, or it was what was happening during the track mode is not of a very important for us. What's important is the value that we hold on the capacitor. That's the value that is going to go to the ADC and we'll work on it. So the value that we hold is what is important for us. This is what we need to understand. Any question on this?
Ma'am?
Yes.
I wanted to ask, initially in track and hold, when there is a peak, right? Why is there a peak over here? Could you please explain this part?
This one?
Yes.
Yeah, basically here we were holding a previous value from before, and now assuming that they are aligned here. Okay, so that is the starting of a tracking phase. So now it will I mean, ideally, in the ideal case, it will directly go and follow the VN. So this is the VN is in the dashed line. So that's why it went up to follow VN. Is it that clear?
Yes. So after when we track, then it falls back down.
Yeah, because now it's following it. I mean, the V input is going down. That's why it's going down with it. Because we are just following V and we are tracking it.
All right. I got it. Thank you.
Thank you. Any other question?
Ma'am, but we need sample and hold for in this sampling concept instead of track and hold.
In reality, we mostly use track and hold circuits. They are referred to as a sample and hold. In reality, they are track and hold, but generally known as sample and hold, because again, you don't care what's happening in the tracking mode. That's of not importance for you. What you care about is the value that you hold. So whether it's a sample and hold or a track and hold, your ADC will capture the holded value.
Okay, ma'am.
That's why I mean, we don't care is it track or it's a sample and hold, because we will work on the holded value. Okay. Now, in reality, yes.
Could you please explain the waveform for sample and hold circuit?
The waveform of what?
Sample and hold circuit.
This one. So here, basically, you sample this value and you keep it until the next clock cycle. Now, the next value from the VN that we sample is the one down here on the dashed line. So we sample this value, and then we hold it until the next cycle. Now, what is the value on the VN? This is the value of the VN from the dashed line. We sample it and we hold it until the next clock cycle. Now, on this next one, what's happened? We sample this value and we hold it until the next cycle. So at, let's say, every edge of here, let's call it, seems to be it's working on the falling edge if we are assuming this clock. So you see what is the value of the input at that particular time, and then you hold it to the next cycle. Look at the input, what it is at that time, and hold it for the next falling cycle, falling edge of the clock. Okay, so now in the ideal world, we assume that this switch is basically have a zero resistance, and therefore the switch will just close for the very short time. And we are going to hold the capacitor on the hold the voltage on the capacitor until the next sample time comes. But that's not reality. We cannot have that much short time of pulses. So what happens is that we have a 50% duty cycle clock in most of the cases, and V output basically tracks V input half of the clock cycle when the switch is closed. And basically we try to capture the exact value of the VN at that particular instance when the switch is open. So once the switch is open, that the last value that was stored on the capacitor, we want to hold it until the next clock cycle comes. And therefore, this is what known as track and hold. Again, we usually refer to it as even sample and hold. One more time, in track and mode, the clock is high and the switch will have a low impedance. Therefore, the V output is almost equal to Vn. And in the hold mode, when the clock goes low, the switch becomes open and the V output maintains the last value that was stored on the capacitor. So this is one more time, you can see it yourself, what's happening here. Now there are, in reality, practical issues that come with track and hold or sample and hold circuit. And in order to make a good ADC and a good mixed signal design system, we need to cater those issues and try to mitigate their effect as much as possible. And this, I mean, you can study this topic for very long. It's very extensive topic to study the practical issues of sample and hard circuit. And there's a lot of research on this thing has happened. And I think still you may find room for improvement yet. So the first is that basically the switch here is the simplest form we represent it or we implement it with a MOS transistor, whether NMOS or a PMOS transistor. And therefore it has a finite resistance. So it's not a zero resistance. There is some value of the on resistance for this switch. And it's also the presence of this resistor cause that the bandwidth of this circuit is also limited. And therefore it takes some time to reach to the desired output. We're going to discuss all of this in detail. And as well as that, the on resistance is also not a linear resistance, it's a non-linear resistance, therefore it will cause distortion. And there is also the clock jitter problem. And we have a switch charge injection and clock feed through. We'll discuss these in details. So the first to start with is the sampling circuit, basically the noise of this circuit. Now this switch, basically again, it's implemented with the MOSFET transistor. Let's say in the simplest is an NMOS, and it has an on resistance, and this on resistance will have a noise on it, a thermal noise. That's basically, this noise is given by 4 kT times R. So this is the noise mean square value. And now this noise is going to be sampled on the capacitor value. And it will, since the capacitor and the presence of a resistor here and capacitor, they will form a low pass filter behavior. Therefore, we will not have this exact, the same value of the noise sampled here. It will be filtered with the low pass filter that we have formed through the capacitor and resistor, and therefore it will have a different total noise variance that's equal to KT over C. Now we will see how this came from, where did it come from. And as you remember, we talked about it last time that in high resolution ADCs, with this sampling circuit at sample and hold circuit at the front of it, the KT over C noise, which is the thermal noise, dominates the overall minimum signal handling. Can someone explain what does this mean? Without, I mean, don't want you to explain from where KT over C came. Just tell me this, I mean, I discussed it last time, so I just want to know, did you understand it, or what does it mean?
Ma'am, can you repeat the question?
The question is saying to explain this sentence that in high resolution ADCs with having a sample and hold circuit at the beginning, this noise, the thermal noise, dominates the overall minimum signal handling. What does this mean?
Ma'am, you explained that as the resolution increases, the
Yes.
quantization noise decreases.
Yes.
So the thermal noise, which is already present, it becomes more dominant compared to the now low quantization noise.
Yes, excellent. That is what this is exactly meaning here. So now we will see the effect. Thank you, Roshan. We will see the effect of this one, how it came from. So basically this noise, again, is coming from the switch on resistance, because it's the MOSFET. It has an on resistance when it is operating on the linear region, and it operates in the linear region when it is acting as a switch. If you remember, it operates in the saturation region when we want it to act as an amplifier. And when we wanted to operate as a switch, we operated in the linear region or in the active region. Okay, now this on resistance, it has a noise, and this thermal noise is defined, I mean, to be the mean square of this noise is 4 kT times R. K is Boltzmann constant. It has this value 1.38 times 10 to the power minus 23. T is the temperature in Kelvin, and R is the value of this resistance in ohm. Okay, now this noise, assume it like a voltage source here or a voltage, it's going to be sampled on this capacitor that is here. Now, since this R and C, they form like a low pass filter, this is V out. So not entirely, I mean, it will be basically filtered noise on this capacitor stored. And how to find the value of this noise? We multiply the total noise with the noise bandwidth. And basically now what is the question? Now we know this is the noise. What is the noise bandwidth? Now there is, if you have studied it before, I don't know that, did you or not? Basically the noise bandwidth of a low pass filter, first order low pass filter, is given by pi over 2 multiplied with the bandwidth of that filter, the cutoff frequency of the filter. So this is, I mean, a definition. I don't know if you have covered it before or not. If you later, I mean, interested, I can guide you, or you can search it online. It's available. How to find the noise bandwidth of a first order low pass filter. You can find it out. It's equal to pi over 2 multiplied with the cutoff frequency of the filter. So now, in order to find the noise that will be sampled on the capacitor, we multiply the noise bandwidth with the 4 kT over C, and the pi goes with the pi, 4 goes with those two together, R goes with R, and therefore we end up with the kT over C. And this is a very famous term that you should know. So the noise on the capacitor, the mean square of this noise is 4 kT over C. This, you should know that this is the definition of the thermal noise. This is the value of the thermal noise for a sample and hold circuit, a simple sample and hold circuit here. Okay, so this is the take off from here, this the value of this noise. Now, so what do we assume the spectrum of the sampled noise? So we assume that this KT over C noise will show up as a flat spectrum in the band from 0 to fs over 2, as long as the cutoff frequency of this low pass behavior largely exceeds the sample rate. Means if, so we assume it to be, this is fs over 2. We assume it kind of a flat in this bandwidth from 0 to fs over. Keeping in mind, I mean, given that the cutoff of this filter 1 over RC is way above 1 over RC here, is very far, I mean, more greater than the sampling rate. This is fs here, so this should be greater than it. Otherwise, if you are cutting it here, then you don't need to include that part of the noise. But I mean, having that said, then it might not work for you if the bandwidth of this filter is so small. We will see why is that.
Ma'am, can you repeat that part, please?
Yeah, I said that you should, the cutoff frequency of this filter, I mean the bandwidth of this filter has to be larger than my sampling rate, larger. So 1 over RC should be greater than fs. Otherwise, I cannot make this assumption that it is a flat within from the bandwidth of 0 to fs over 2. Okay? I mean, we are assuming it to be flat, this noise KT over C.
Okay,
Now,
thank
yeah,
you.
yeah. Now we will see also that selecting this bandwidth is also a tricky thing. I mean, there are a lot of issues that they are all related to each other, and we need to be careful when we select any parameter in the circuit. Now, since this thermal noise is there, we need to see how this is going to affect my something very important parameter for me, which is my SNR. If you remember, what is SNR? It's my signal to noise ratio. So for most of the ADCs, we select the value of C is so that to have a thermal noise smaller than or equal, or in sometimes larger than the quantization noise. So if your let's say quantization noise, let's say, is not so dominant here, you need to make sure that you have a certain level of thermal noise does not make your design further lower. So you need to take care of the value of this C so that you don't become dominant with the thermal noise. Now, how to do these calculations? You remember that we studied that the total quantization noise from last lecture, that it's equal to delta square over 12. What is delta? What?
The levels between the distance change between the levels. Right?
Yeah, so it's the LSB of my ADC. Yeah, and it's given by delta equal to V full scale divided by 2 to power n. Okay. Now, yes. Just give me 1 second. Okay, I just want to take a pause for a minute to take a snapshot of the attendance. And I just want to tell you that within next week, since we hopefully will be on campus, you should expect a quiz. Oh, this is not happening the way I want. Just okay, now we come back here. So we remember that the quantization noise is basically delta square over 12. and delta is the V full scale divided by 2 to power n, which is my LSB of my ADC. So now I want to make sure that my thermal noise is less than or equal to my quantization noise. How to do that? This is my thermal noise. It should be less than my quantization noise. Is that clear to everyone what's happening here? So I want to select a value of a capacitor that guarantees for me that my thermal noise is less than my quantization noise. Okay, so now the thermal noise is KT over C. Quantization noise is delta square over 12. So I just do the rearrangement here. I take C on one side and rearrange. So you will get that your C should be greater than 12 times KT 2 to power 2n divided by V full scale square. Now here just we opened this coming from the delta square. Okay, so now you can see this table is comparing the values of the capacitor that required for a different resolution. B here is the same as N, the resolution of my ADC. So now if I have N-bit ADC, 8-bit ADC with a full scale of 1 volt, I need, what is this? 0.003 picofarad. It's quite low, manageable. Okay, if you need, if you have a full scale of 0.5 volt, you will see a larger value of capacitor. Now, if I go, you can see these numbers. If I go to high resolution ADCs, now there the quantization noise goes very low, as you remember, at higher resolutions. So in order to have a very small or very low thermal noise, I need to have very large capacitor. So my KT over C, it's an inverse relation between C and the noise. So I need a very large C in order to have the term KT over C very small. And 52,000 picofarad is a huge number that I cannot integrate on chip. So what should I do in this case? If I want basically to have a large resolution ADCs with this problem. So in this case, typically I don't use an Nyquist ADCs. There are different types of ADCs that we will study later, and they are called oversampling converters or oversampling ADCs, sigma delta ADCs. They have different techniques to use that they don't need that much large capacitor in order to achieve this high resolution. Okay, is this clear what's going on? Any question?
Ma'am, I have 2 questions.
Yes.
One from the previous one, basically we have to choose a capacitance value such that the thermal noise is going to be less than the quantization noise.
Yes.
Could you please explain why do we need to do that?
You need to do that because you don't want to ruin your design. I mean, you are, for example, assuming that you will be dominant by your quantization noise, and you make your own design, and then you end up with, when you add this sampling and hold circuit without taking care of which value to select for the capacitor, then your thermal noise suddenly dominates your performance, and you get a very poor SNR that will basically not work for you as you intended. So you need to make sure that you are not dominated by the thermal noise, and you make a proper choice of your sampling capacitor.
But isn't quantization noise also detrimental, or is it because we are working in higher resolution that it's not very large so that it can mess up our circuit or something?
What do you mean by that? Means now you are making this design, N is coming in the equation. So you are knowing what is your quantization noise based on your selected resolution that you have. You just want to make sure at that resolution, you don't have more thermal noise than that your quantization noise.
Okay, I got it. Ma'am, also the next slide, could you just repeat the part where you were explaining that you cannot have that large capacitance? After that, I got a bit confused.
Yeah, basically, we have, when we implement the capacitors on chip, the value of the capacitor is basically means area. Okay, so smaller, you have a like, let's call it a sheet capacitor that has a certain capacitance value per width and length. And if you want to have that large of number or a value of capacitor, you need to integrate all of these together in order to achieve the value of capacitor that you're aiming for. So if you go for a very large capacitors, means more than, let's say, 10 pico, or I mean, then you go for that requires a lot of area. Okay, and area means money, because
Okay.
every millimeter of your chip area costs you a lot of money. So for example, if you go in 180 nanometer technology, 1 millimeter area square is $1,000. If you go for a higher, a more advanced technology, lower nodes, then in 65 nanometer, it's $5,000 per millimeter square. So you can see that you cannot just put as much capacitor value as you want. It will cost you a lot of area. I mean, that's other issue is also power consumption, and because the value of capacitor will also do something with your power. So if you increase C, you will also increase your power consumption. So therefore, you need to be careful when you select those values. You cannot have that much larger capacitor on. That's why we are typically below, limited to around 14 bits of Nyquist-Thread ADCs. If you want to go to higher bits, you use the sigma delta ADCs, because you cannot integrate that much large value of capacitor on chip. Okay.
Okay, yes, thank you.
Any other question?
Yes, ma'am. Could you please explain how our sapling reduce the size of capacitor?
How your sampling reduce the size of capacitor? I didn't. You can see here there is no clock coming. Clock is not related here.
Excuse me, ma'am. We prefer to use 1 volt as a full scale voltage instead of 0.5 volt.
That depends on your application. So I mean, if you go for a lower technologies, you go for a lower voltages as well.
Right.
Yeah, so basically that depends on which application, which technology available for you, and what are your trade-off. So there is no, let's say, one definite certain voltage that you can use. I mean, you have different, you can use both, but it depends on your application. So there is no definite answer here.
Because you can see that for 14-bit ADC, we would prefer to use 1 volt instead of 0.5 volt due to the capacitor size and
Yes.
like that.
Yeah, I mean, also this is the most simplest, let's say, form of sample and hold. There are more other techniques, and now this is, let's call it, I don't know how many years old technique. There are millions, no, not millions, too much large number. There are many advanced form of the sample and hold circuit that they propose different techniques to reduce this circuits, this capacitor size. So in this simplest form, not very widely used. You will find many different forms of it. So that's why, I mean, just this is to give you an answer, I mean, a quick overview about it. So that I mean, so I cannot tell you you should not use smaller V full scales, but you should be, I mean, select the choices of your designs properly. Okay, now let's take this example. So you have supply voltage of 1.2 volt, and you have a sinusoidal signal that have a 500 millivolt peak to peak. Okay, and please nobody send on the chat. I cannot read while I am writing. So I have 100 megahertz clock and 500 millivolt peak to peak signal. We have an SNR. We need an SNR of 72 dB. So what should be the value of the capacitor that we should select here? Take 1 minute to think about it. Okay, so we have a signal of 500 millivolt peak to peak. So we need just to remember that our noise, SNR is equal to 20 log of V signal RMS over V noise RMS. If I am using a power, then it will be 10 log of signal power over the noise power. Okay, so how can I find this V signal RMS? If you remember, I told you for a sine wave signal, it's the value of A. A is the half of the height here. Divided by square root of 2. So it will be the 500 millivolt divided by 2 to get A, and divided by 1 over square root of 2 to get the RMS value. Now, so SNR, I want it to be 72 dB. This is a 20 log. So what is this value becomes out to be? 177 millivolt RMS. So this is 177 times 10 to power minus 3 V RMS divided by V noise RMS. So I need to open this, and so I divide by 20 both sides. I take 10 to power 72 divided by 20, how much? 36, 3.6. So 10 to power 3.6 gives us 4,000. No, what times is it? Yes, so basically we get the V noise RMS. After you do this math here, it will become how much? 44 microvolt RMS. And this is basically equals to what? Square root of KT over C, because V noise RMS square is equal to KT over C. So now you need to, K is a Boltzmann constant, 1.33, 1.38 multiplies with the 10 to power minus 23. T is a temperature of 297 Kelvin. And therefore you plug in these values here, you get C equals to 2.15 picofarad. Is this making sense? Any question?
Ma'am, in all the questions, we will be considering room temperature.
Yes. Unless otherwise stated for you.
Ma'am,
Yes.
the supply voltage 1.2 volts, does that not have any function? It's just mentioned for the
Yeah,
sake
it's
of
mentioned here, but I mean, if I asked you, for example, regarding what should be made less your, so here I'm giving you SNR, but what if I gave you a different value? I told you that I want to select my thermal noise to be less than my quantization noise for this certain number of bits. Then you will need to use that supply voltage, or assuming that your V full scale. Okay, so I just solution. Now let's move more to other issues. So basically, we were
Ma'am,
yes.
can you also tell us a question like that in which we will apply the full scale voltage?
Yeah, it's similar to what we were doing here in this thing here. I mean, just if I told you that you are needing the V full scale in order to find the delta. So if you were comparing your thermal noise with to be less than your quantization noise.
Okay.
Yeah, I mean, we were assuming here that the tracking basically, once you close the switch, directly your output jumps and it becomes equal to your input. And that's not reality. I mean, this is assuming that you have a zero resistance for your switch, which means an infinite bandwidth, which is not a reality. So in reality, we have a finite bandwidth that will cause your, if I can zoom in here. So the V output will rise to and then start to track. So it will basically here rise and then in order. So there will be some delay time. And you know that basically when you have an RC circuit, so you have a tau that's a time constant equal to RC. And this RC is inversely related to your bandwidth. So if you have a large time constant, this means you have a smaller bandwidth. So ideally, what we want to have is that we have a larger bandwidth for our sample and hold circuit so that we can track fastly. Then we will have a shorter time constant that will basically allow us to reach to the desired value quickly. Okay, you know that also the bandwidth is 1 over RC here. So they are inversely related to each other. So when you have a larger bandwidth, you will have a smaller time constant, and the time constant decides how the time that you are going to rise your voltage to reach to the desired level. And from where this came, this again came from the switch on resistance. So the low pass network determines the tracking bandwidth. And again, the tracking bandwidth determines how promptly V out can follow V input. And this basically came from the switch on resistance. So the R on is, should we just, it's 1 over mu n COX W over L with the VDD minus V threshold minus V input. So this is the switch on resistance. So when the switch is on, this is the resistance that it basically have. So it depends on the VGS of this or the overdrive voltages, which is the VGS minus the V threshold. So this, no, VDD minus V input here. This is VDD is the value of the clock on the switch when it is high. And this is the V input voltage. So the S, and this is the gate of the switch. So VGS is VDD minus V input minus V threshold is the, this is called V overdrive voltage of the switch, multiplied with the mu n COX with the W over L, the size, the width and the length of the switch. You can see now that the on resistance is basically dependent on the input voltage. And again, we said when the switch on resistance or something depend on the input voltage, it causes distortion. And we can see here that the relation is also not linear relation, it's non-linear resistance, therefore. Now this can be, not very important problem if you make the bandwidth is much very high, but what is the issue of making the bandwidth very large? You remember from the sampling lecture, if we make our bandwidth large before we sample the signal, if it was large bandwidth, what happens?
Ma'am, the overlapping will occur between the
Yes, the noise folding. So the noise at higher frequencies will come back to our signal bandwidth. So we have to be careful when we do that. Okay, so now how can we basically select lower or higher bandwidth with a lower time constant? We can select shorter L, larger W, larger, this is V overdrive. And this all will decrease this, and smaller Vn. This will all decrease my on resistance of the switch. Now, I can also decrease this RS, which comes from the source, from the input side. If my input is coming from another amplifier, or I can add a buffer with a very low output impedance, but this will require me to carefully design that buffer to have a low output impedance. So if I achieve all this, I can get more speed to reduce these resistances. I mean, this capacitor, we said we are limited with selecting it by the thermal noise. So we cannot go for a low value of capacitor in order not to get a higher noise. So you can see here you have a trade-off between the noise and the bandwidth, the thermal noise and the bandwidth. If you want to decrease, if we want to decrease the C, no. If we want to decrease C to get a larger bandwidth, we have then my noise, thermal noise will go up. So there is a trade-off here. Now what, again, if I increase W and V overdrive of the switch that was here in order to reduce R on, what happens? I will have large channel charge. And this will cause track and hold errors that we will discuss in a while. So you remember from the course, I think, of devices, that in the transistors, when you on the transistor and you form a channel between the source and drain, charge is being stored in that channel. The more area of the channel width of the transistor, you will have a larger charge. And the presence of this charge when the switch closes basically will cause issues to the voltage that I am storing on the C out, but we are going to discuss them. Okay. Now, before going into that, let's further move into the bandwidth in order to study how much bandwidth I am allowed. Okay, so again, the resistance R of the switch turns the sampling network into a low-pass filter with a finite time constant, which is equal to R and C. Now, assuming that Vn is constant or changing very slow within that sample period, we need to allow enough time for the output to settle to less than 1 ADC LSP in a half of a clock cycle. What does this mean? Can you see this plot down here? Now, this is the half of the clock. So we want the V output. This is the blue line is the V input. Within half of the clock cycle, when the switch is closed, I mean, this switch is connected, we want V out to track V input and reach to a value that's different. I mean, the difference here between V input and V output should be less than 1 LSB. And the time for doing this should be in less than half of TS. Again, so why I selected half TS? I selected half TS because this is the entire time when the switch is closed. Okay, so while the switch is closed, I want V output to reach to the value of the V input while the switch is closed. If it happens after that, then I'm not capturing the right value of the VN. That's something not good. Now, why I want it to be less than half LSB? So that I be more accurate. If I selected, if it is within more than 1 LSB, this means I am going to have a different code for my output digital signal, and that's something incorrect. Is this all making sense to you or no?
Yes, can you please repeat the last point?
Yes, so basically, we want the V output to track V input while still the switch is closed. And how long the switch remains closed? It remains closed for half TS. This is all the cycle is TS. Okay, so this is the first part. Now the second part, how much difference between V out minus Vn? The difference between them should be less than half LSB. 1 LSB, or even you can go to less than half LSB. It depends on how much accurate your design wanted to be. Now, why is this? So that once I will take the sample to my ADC, if it was the difference between them more than 1 LSB, this means I am going to reach to a digital code that's wrong. That's like, you know that each 1 LSB causes you to have a new digital code. So if the difference between them is more than 1 LSB, this means I am going at the output of the ADC have a different code from what my original VN was. So this means there is an error. I mean, I am generating a code that's belong to a different value of the V input. Why this has happened? Because my track and hold circuit was not able to track the correct value of the V input within the required time. So in order to guarantee that it can track within a required time, I should have sufficient bandwidth of my track and hold circuit. So this will set a design requirement on the value of the switch on resistance that you can select. I mean, okay, is that making sense?
Yes, Miss.
Thank you.
Ma'am,
Yes.
will that does not depend upon the resolution of our ADC, like about the LSB thing.
Yeah, it will depend obviously on your LSB. Yes, the resolution of the ADC. Yes, they are linked with each other.
So in order
if
to
you
track
have,
it,
yes.
So in order to track it accurately, what we need to do is that we have to alter the value of resistance before the switch, right?
Yes, you need to make sure that your switch on resistance remain within a certain size. Stay the maximum resistance that you can have should be lower than a certain value in order to guarantee that this is basically happening, these conditions. So now let's say you selected your C from your KT over C noise. Now you need to decide the value of the R of the switch. So how you are gonna do that? You will basically find the tau function, acquisition time. I'm going to describe here. So your tau is your R and C. So we found C. Now we should find the value of the R on. Let me explain this slide for you here. Okay, so we assume that we have again a linear settling of a first order system. Now we basically, what do we have here? Assume this is my V final that we want to reach to it. And this is the V initial that we are having here. And I want to change the color. Okay, so this is the V of t by at any point on time. This is the axis here is t time, and the time it takes to V final to reach, sorry, to the V of t to reach V final is capital T here. Okay. Now at this time when it's t, so this point is V of capital T. Okay, so now what is happening here now? You know that basically V of t is equal to V initial, the starting point, plus V final minus V initial, the trip that it has to make with the settling minus 1 over T over minus tau. This is coming from that V out equals to Vn 1 minus e to power T minus tau. This is how you find the settling time of the first order system. Okay, now I rearrange these things in order to find the value of the t. What does t here means? The time it will take to reach to this desired value. So now we can see that this time is depend on the delta V. The delta V is the jump that we are going to have here. So this is the delta V, which is V final minus V initial. This is delta V. And the error is basically V final minus the V of t at that particular time. So V final minus the value that we have really reached to it. Now we want this error, we just said, to be less than 1 LSB. Okay, and the maximum error will have, or the maximum jump that we can have, is when this difference between the final and the initial value is a V full scale. So I'm just jumping, let's say, from 0 to V full scale. And I want at the end of this time T capital to reach to a value that is just less than 1 LSB difference from the V final value. Is that making sense? No?
Ma'am, you should repeat that, ma'am.
Yeah, basically we want V out. I mean, it's saying you need to know this relation. If you don't know this relation, you will not be able to link this information that is here. So basically it tells you how much, what is your V output as a function of time, your input voltage that you have, and how much time it's going to reach to the desired input voltage, how it will follow it. Okay, now we have, from this equation, we just have that we have an initial value starting point. So that is that's why we are adding it here. And the maximum volt, or the voltage difference that we have here. So basically we are trying to find this T here. And we have given it the name to be capital T. So we rearranged the whole equation, get rid from the exponential part, and we got that T equals tau, natural log of the V final minus V initial divided by V final minus V tau, V of t, sorry. Now, okay, let me get from this one. Now, the thing that you should know here is that what is the worst case scenario that is happening? The worst case scenario is that when I need to make the biggest jump. When does this biggest jump happens? When I am at, let's say, 0 and I want to jump to V full scale. So that's why delta V is a V full scale minus 0, which means a V full scale. And how much error I am okay to tolerate? My error should be less than 1 LSB. So my V final, the final value that I want to reach, minus the value that I have reached to it, their difference should be less than 1 LSB. And the total jump that I am making is, which is delta V here, is I am substituting it with a V full scale. So now I want again to find this capital T. Here again, they are naming it to be T acquisition time. So it should be T natural log with 2 to power n. From where this came 2 to power n, I just substituted that delta V is equal to V full scale and epsilon equals to delta, which is V full scale divided by 2 to power n. Now, when you will put V full scale over V full scale over 2 to power n, this will go with this one and 2 to power n will come up. And that's why it came out like this. So now if you take n outside of the natural log and find the natural log of 2, it comes out to be 0.69 multiplied with n and tau. Okay, now what did we get out? I mean, what is the takeoff here? Takeoff is basically that this T acquisition is going to basically depend on your tau and your resolution and this constant value. So now if you want, let's say, an accuracy of 1%, accuracy of 1% translates basically to 7-bit. How does this? It's 1 over 2 to power 7, and this is approximately 1 over 128, which is almost equal to 1%. I mean, it is less than 1%, but just giving that. So if you have a 7-bit ADC, your acquisition time is basically more than 5 times of a time constant. So now, knowing this, you will select, you can decide the R on based on, this is the value of the tau. And your T acquisition is your basically half time, let's say a maximum value of it is your half of your TS. Now, if you go for a higher resolution, 10 bits, which means 1 over 2 to power 10, which is almost 1 over 124. This is almost equal to 0.1% accuracy. And this requires a 7 tau. You can see now when you, every time you're increasing your accuracy, you are reducing your LSB size, and therefore you need more time for your output to follow your input within less than 1 LSB value. Okay, so this will decide, I mean, a minimum requirements, sorry, a maximum value of your R on that you can select. Now let's see this example. So if you have a sample and hold circuit that should settle within 1% of its final value at 5 microseconds, what is the maximum resolution and speed with which an ADC can use this data, assuming that the ADC is ideal? Okay, so we said maximum first this T acquisition is basically should be less than half of the sampling period, yes? So if it is a 5 microsecond, means less than half of TS, and therefore TS should be greater than 10 microsecond, and therefore your FS, your clock, should be what? Greater or less than 100 kilohertz. Sorry, great. No, less than. Is this clear? Any question on this
Yeah.
part? Yeah, so again, we want my acquisition time to be less than half of the clock cycle, so that I can settle within the hold, the tracking period. Otherwise, it will be something, I mean, not a correct behavior. Now, since it is settled, this happens within 1% accuracy. Now, this 1% accuracy related to the LSP size. Okay, and this is what we just said in the previous slide. So 1% accuracy related to 7-bit of your ADC. So therefore, the maximum resolution of this ADC is 7 bits. Okay, so just solution as simple as that. Any other question? Okay, now we just want, let's continue on this. Basically, we have discussed that the resistor is not a linear function of the V input. And therefore, if you want to, when your V input becomes very near to the VDD minus V threshold, your R-on suddenly shoots up very high. And this basically, the nonlinear behavior here causes a distortion for your output. So if we just look at this example here, now assuming I have a larger, in the blue line, in the black line, sorry, I have a larger switch width. So this value is large, and therefore I will have lower effect to this part here. You can see when my Vn goes high, I am slightly not tracking it correctly, but it's still good enough. If you look at the smaller switch width, now this will have a more effect, and therefore when your Vn becomes large, your R output is shooting up high, and therefore your bandwidth becomes smaller, your RC time constant become larger, and you are not tracking the input voltage correctly anymore. And that's basically cause a distortion in your output spectrum that you don't want it to happen. Just let's finish with this example. So if you want to calculate the maximum and the minimum value of the switch on resistance, assuming that beta is mu and COX equal to 550 microamp per volt square, W over L is 10, V threshold is 0.7, VDD is 3 volt. So how should calculate the maximum and minimum Vn?
Ma'am,
Are on.
ma'am, what this beta represents actually in this formula?
Mu and COX.
No, ma'am, it means that what is actually beta in this thing? Beta means it affects which thing, ma'am, in the formula?
I'm telling you, it is the product of mu and COX. Which is in the equation.
Okay, okay.
Okay, so how should we solve this? So beta is also coming here in your equation. So this is the same as mu1 COX. Some books use mu1 COX, some other books use beta. So again, here beta, they are defining it. Okay,
Yes,
so
when we have all the values, so we will put it in the formula just.
yes. So you again, you have all the values. You need just to know when to plug in, to know the maximum and when the minimum. So it is 1 over mu(n) COX or beta as you want to write, W over L. Now VDD minus V threshold minus Vn. Now the maximum will happen when Vn is a 0 or a 0.5 volt.
V in 0.5 volt actually.
Yes, when you this term goes smaller, your R on will goes up. So R on will be max when Vn equals to 0.5 volt. And this is 1 over 50, 10 to power minus 6 times 10 W over L with VDD is 3 minus V threshold 0.7 minus 0.5. So now you find the value. And when R on minimum is when your Vn is equal to 0. And this again happens like this. 10 W over L with a 3 minus 0.7 minus 0. Now this term is going to become larger, therefore your R on will be reduced. Now you can plug in and find the values. Any question?